Greetings and welcome to lecture number 12 on the course Introduction to Fourier Analysis. On the previous lecture, we defined the space of Schwartz functions, also known as rapidly decreasing functions, and discussed some of their basic properties. For example, the class of Schwartz functions is invariant under differentiation, multiplication by polynomials, and convolution. However, all of these basic properties would also be true for the smaller space of so-called test functions, often denoted by a calligraphic D, which consists of smooth and compactly supported functions. So, what is the benefit of studying Schwartz functions over test functions? The reason has to do with how Schwartz functions interact with the Fourier transform. On this lecture, we will prove the following theorem 3.7. First, if phi is a Schwartz function, then also the Fourier transform of phi is a Schwartz function. Recall from proposition 3.4 that Schwartz functions are L1 functions, so the Fourier transform here refers to the Fourier transform of L1 functions. Second, if phi is a test function and also the Fourier transform of phi is a test function, then phi is the zero function. A bit less precisely, theorem 3.7 states that the Fourier transform preserves the class of Schwartz functions, but not the class of test functions. However, note that since test functions are Schwartz functions, it follows from the first part of the theorem that the Fourier transforms of test functions are Schwartz functions. We will start with the proof of part B. The proof will require one key result from a basic course in complex analysis. If you haven't studied complex analysis, don't worry, this proof will not be a part of the course's core material. The theorem from complex analysis we need is the following. If f is an analytic function defined on the complex plane C, and f vanishes on any infinite set with an accumulation point, then f is the zero function. The infinite set we are interested in here is simply a segment of positive length on the real line. So, in particular, the theorem states that if an analytic function f vanishes on a segment on the real line, then f is the zero function. To make use of this result, we fix a test function phi, and we consider the complex-valued function hat phi defined on c to the power d by the formula hat phi of z equals the integral over rd of phi x times e to the power minus 2 pi I z dot x dx. This formula looks exactly like the usual formula for the Fourier transform of phi, the only difference being that now the argument z can lie in z to the power d and not just in rd. It turns out that the function hat phi is separately analytic in all of the d complex variables. In other words, if one fixes an index j between 1 and d, and also fixes complex numbers z1 to zj minus 1 and zj plus 1 to zd, then the function z maps to hat phi evaluated at z1 through to zj minus 1, zj plus 1 through to zd is an analytic function of one complex variable, namely z. This is easy to check, for example, by using Morera's theorem from basic complex analysis. Now let us prove theorem 3.7b, which stated that the only test function whose Fourier transform is also a test function is the zero function. Fix a test function phi on Rd and assume that also the Fourier transform hat phi is a test function. This means in particular that the support of hat phi is compact. One has to be quite careful what this assumption means. It means a priori that the Fourier transform defined on Rd has compact support. We are not assuming, to begin with, that the extension of the Fourier transform to c to the power d would have compact support. This will, of course, be a consequence of the proof once we know that phi is the zero function. From our compact support assumption on Rd, we can infer that if j is any index between 1 and d, and xi1 to xij minus 1 and xij plus 1 to xid are fixed real numbers, then the analytic function z maps to hat phi evaluated at xi1 through to xij minus 1, z xij plus 1 through to xid vanishes on an unbounded interval on the real line, namely outside the compact support of hat phi. Hence, this analytic function of one complex variable is the zero function by the complex analysis theorem we cited a bit earlier. In particular, this function vanishes on the whole real line and not just an unbounded interval of the real line. Since the same conclusion holds for every index j between 1 and d, we conclude that the Fourier transform of phi vanishes on Rd. After this conclusion, it only remains to apply the so-called uniqueness theorem for the Fourier transform, which we will prove in a couple of lectures. This theorem will state that if phi is an L1 function whose Fourier transform vanishes identically, then phi is the zero function. Putting these pieces together, we have now shown that phi is indeed the zero function, as we claimed in part B of theorem 3.7. We then move to the proof of part A of theorem 3.7, which claimed that the Fourier transform of any Schwartz function is again a Schwartz function. The proof will be based on a number of independently interesting formulas for the Fourier transforms of L1 functions and Schwartz functions. We record all of these in proposition 3.8. Some of them will probably look familiar to you from the theory of Fourier series and coefficients. Let f be an L1 function and let tau and xi be vectors in Rd. The first statement says, informally speaking, that the Fourier transform turns translation into modulation, which means multiplication by a complex exponential. More precisely, consider the function f tau whose value at x equals f evaluated at x minus tau. Then f tau is again an L1 function whose Fourier transform at xi equals e to the power minus 2 pi I tau dot xi times the Fourier transform of f at xi. The second statement in the proposition is the converse of the first one. If the function f is multiplied by the modulation e tau of x equals e to the power 2 pi I tau dot x, then the Fourier transform of the product at xi equals the Fourier transform of f evaluated at xi minus tau. The third part of the proposition should look very familiar. It states that the Fourier transform turns derivatives into multiplication by polynomials. If f is now a Schwartz function and alpha is a multi-index, then the Fourier transform of the alpha derivative of f at xi equals 2 pi I xi to the power alpha times the Fourier transform of f at xi. The fourth part of the proposition is a converse to the third part. If f is again a Schwartz function and alpha is a multi-index, then the Fourier transform of f multiplied by the factor minus 2 pi I x to the power alpha evaluated at xi equals the alpha derivative of the Fourier transform of f evaluated at xi. Here one should note that the Fourier transform of a Schwartz function is infinitely differentiable, which requires some separate justification. We leave this as an exercise. So the alpha derivative of f hat makes sense pointwise. The fifth part of the proposition states that Fourier transform turns convolutions into products. If f and g are two L1 functions, their convolution is again an L1 function whose Fourier transform at xi equals the product of the Fourier transforms of f and g at xi. For completeness, we mentioned that there is also a converse to this rule, namely that Fourier transform turns products into convolutions. One has to be a little careful, however, since the product of two L1 functions is not always an L1 function. But this rule holds, at least for Schwartz functions. The final part of the proposition tells us in which manner Fourier transform commutes with dilations. If f is an L1 function and delta is a positive real number, define a new L1 function f delta by setting f delta of x equals delta to the power minus d times f evaluated at x divided by delta. This kind of normalization might look familiar to you from the way in which approximate identities are often defined. The Fourier transform of f delta at xi equals the Fourier transform of f evaluated at delta times xi. Here you can see an illustration of the last part of the proposition, applied with two parameters delta 1 and delta 2. When the parameter delta decreases, the function f delta concentrates more and more around the origin, but always has the same L1 norm. The formula in the last part of proposition 3.8 tells us that the Fourier transform of f delta behaves in precisely the opposite way. As delta decreases, the Fourier transform of f delta becomes more and more spread out. To get the idea, try setting delta equal to 0 in the formula of part D. You should think that f0 is an infinitely tall and narrow spike at the origin, whereas f hat evaluated at 0 times xi is identically equal to the constant f hat 0, which is equal to the integral of f. The proofs of all the formulas in proposition 3.8 are nothing but straightforward calculations, and we leave them as exercises. The formulas might be difficult to remember precisely, at least for me, but it is much easier to remember the principles. Once more, Fourier transform turns translations into modulations, derivatives into multiplication by polynomials, and convolutions to products. We can now prove part A of theorem 3.7. Let phi be a Schwartz function. We claim that the Fourier transform hat phi is also a Schwartz function. As we already mentioned while discussing proposition 3.8, it takes a bit of effort to show that hat phi is infinitely differentiable, but we leave this as an exercise. So all that remains is to show that all derivatives of hat phi and all products of hat phi with polynomials are L infinity functions. To do this, let alpha and beta be arbitrary multi-indices. We claim that the function xi to the power beta times d alpha of hat phi is an L infinity function. To see this, first observe that the alpha derivative of phi multiplied by x to the power beta is an L1 function. This essentially follows from the assumption that phi is a Schwartz function. However, this condition is not exactly the same as the definition of a Schwartz function, first because it is a claim about L1 instead of L infinity, but second because the differentiation and multiplication by a polynomial are here in a different order than in the definition of Schwartz functions. However, you can check by sufficiently many applications of the product rule for derivatives that the expression here can be rewritten as a finite linear combination of certain polynomials multiplied by certain derivatives of phi. And all of these expressions are L1 functions by the assumption that phi is a Schwartz function and proposition 3.4. With this information in hand, we can calculate the Fourier transform of the alpha derivative of phi multiplied by the polynomial x to the power beta. Using parts b1 and b2 of proposition 3.8, this Fourier transform evaluated at xi equals up to certain not so important powers of 2 pi I, xi to the power alpha times the beta derivative of hat phi evaluated at xi. Therefore, the L infinity norm of xi to the power alpha times the beta derivative of hat phi is bounded by a constant times the L infinity norm of the Fourier transform of the alpha derivative of x to the power beta times phi. But the L infinity norm of a Fourier transform is always bounded from above by the L1 norm of the function. And we already observed that the L1 norm of the alpha derivative of x to the power beta times phi is finite. Hence, the L infinity norm of xi to the power alpha times the beta derivative of hat phi is finite. Since alpha and beta were arbitrary multi-indices, this proves that hat phi is a Schwartz function. This completes the proof of theorem 3.7. On the next lecture, we will discuss the invertibility of the Fourier transform, which we already used during the proof of part A of theorem 3.7. This concludes lecture number 12 on the course Introduction to Fourier Analysis. Goodbye for now.